than here. And both times he did the same thing, which was he got up and instead of beginning into his talk, he just asked for volunteers. And then, so students would raise their hands out on the art building at that time. And then there were students that had microphones, and they had sections they were assigned to, and they would hand their microphone to one of the students who would raise their hand in their section. And so we ended up with, maybe 10 microphones handed out or something like that. And then Elder Scott would say, okay, I am going to ask you questions. And then you'll give me your answers, and so he would ask the student a question, and the student would respond, and then he would elaborate on the student's question. Well, of course, when he announced that was what he was going to do, there was this little twitter of laughter that went through. You poor suckers. You're about to be interrogated by a member of the 12. And he, of course, would hear it, and he would say, well, I want to teach you something. He goes, those of you who raised your hand and were willing to participate, by raising your hand and being willing to volunteer, you authorized the Holy Ghost to teach you today in ways that those of you who refuse to raise your hand cannot be taught. That willingness to participate, kind of put yourself out there, actually authorizes the Holy Ghost to help you in ways that you can't help somebody who is not willing to do that. And the same thing, I believe, applies to classes. If you're willing to participate, willing to put yourself out there, then you are going to be taught by the Spirit in ways that you won't get taught if you don't. All right, so Beef.
Yes.
You raised your hand. So now, as we do this, and this is no reflection on you, if you make mistakes, that's a good thing. We will learn a whole lot more from the mistakes you make than we will from when you're right. So, mistakes are just the stepping stones to understanding. Now, don't apply that to sin. Right? There's a difference between sin and a mistake. Sin is not the stepping stones to, you can make them stepping stones. So we're really hoping that Beef makes a mistake. But, go ahead.
So the idea behind an upper sum is that we partition our function into some number of subintervals. In this case, there's 4 of them. They don't have to be the same size or anything. And we try and find the supremum of each subinterval. Here, 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 here. Take each supremum, multiply it by the width of the corresponding subinterval, add them all up, and you have an upper sum. If I understand correctly.
Very good, thank you. So, is that how the rest of you understood upper sums?
Yeah.
Now, when they described upper sums, did they say anything about intervals?
Is it a partition?
When
Yeah, a partition. What is a partition?
It's a way of cutting things up so that it's just cutting it into distinct groups where everything's in exactly one group and nothing's out of the group.
Okay. And mathematically, how do we define a partition?
Kind of as
So visually, we're doing what Veith did, which is we're cutting this thing up into segments.
a subset of distinct intervals that cover the whole entire interval.
Did they ever use the word interval?
no, they used
No,
a set of points, including
Set of
in
points.
the
I guess
what you're in.
Finite.
Yeah.
Finite. There we go.
Finite set of
Well, I guess
points.
defines
Newest
very I guess interval.
Now,
It's literally just a finite set of points.
so instead of thinking of these as intervals, what we do instead is we say, well, x0 is going to be a, my left endpoint here, and then x1 is some point there, x2 is some point here, and so forth and so on. x3, and let's see, this one, so this would be x4. So we're just picking a bunch of points, finite set of points, from within the interval, and creating this new set. We require that one of the points be the left endpoint, one of the points be the right endpoint. Mentally, we're thinking of those points as dividing our interval into subintervals. But that's nowhere in the definition. This is just a set of points that comes out of that interval that necessarily includes the endpoints of the interval. All right, good. And then over each interval, we are finding the supremum of the function. And then what do we do with that?
We sum them up.
Do a big sum.
So we do a big sum. And what does the sum look like?
It's gonna be the supremum.
So it's going to be the supremum over the kth subinterval. And
Multiplied by the distance between the 2 points that you're looking at.
Okay.
did they do it that way?
Yeah.
Okay. So this is our width.
Well, that could be negative right there.
Huh?
That could be negative right there. X of k minus 1 minus x of k.
No, why not?
They're increasing order, though.
Yeah, that was the requirement on our partition.
Yeah.
The points were in increasing order.
Yeah, x of k minus x, if you took the previous
No.
term and subtracted by the
Sorry.
term after.
I went backwards.
That's what I meant.
Thank you very much. Yes, I made a mistake. So, yeah, in that direction, so that that's our width. And then this is the supremum of the function. So, sup of f, let's make it f, over what?
The interval x of k to x of k minus 4. Other way around, x of k minus 1 x of k.
Yeah.
That's from 1 up to n.
However many
Yeah.
points there are. So, k1 up to k equals whatever the number of points in our partition happens to be. It's finite, so I know it exists. All right. And the idea of that is that that should be a what? What's the idea behind it?
Approximation of the area.
Yeah, it's going to be an approximation, and in fact, it's going to be necessarily what? How is it going to relate to the actual area? It's going to be an overestimate. So with the lower sum, what's the only thing we change? Yeah, we do a little m sub k is the infimum of that over that interval instead of the supremum. All right. Why do we have to use sup and inf? Why can't we talk max and min?
Because the max and min might not be, well, there might not be a maximum.
Exactly. Now, if f is continuous, tell me something.
We know that there is one.
How do we know there
If
is
it's
one?
continuous, then you're talking about a closed interval.
It's continuous on a closed interval, therefore it has a maximum and a minimum. Yeah.
Yeah.
So, continuous function on a compact set, have a maximum and minimum. All right.
But we haven't made the requirement that we have to do this.
Yeah, we haven't required anything of f so far.
Just defining or something.
Yeah, we just defined what an upper and lower sum is. So, any function would have an upper and a lower sum.
Mm-hmm.
Alright. So, where's the catch?
Wait a second. I have a question.
Yeah.
That is our approximation.
What if,
Mm-hmm.
what if you have a function where you partition it in a way that you have part of it, the function is defined on part of it, but then the function is not defined on another part of it?
Then why are you trying this at all?
Because I'm trying to find the scenario where you don't have an upper sum because it's undefined.
Oh, if you've got, I mean,
Like, let's say
the
you
assumption
have
here is that we have a function that's defined on the interval.
on the
Well,
whole
that's
interval.
all we've said.
And-
Otherwise, why would you be looking at this interval if your function was
And
undefined?
so I'm just, Okay, if you're saying that every single.
We are assuming that-
Is it continuous, does it have to be continuous on those intervals?
No. All we're assuming is that the function is defined.
At every point in the interval?
And there's another assumption that was in there. What else did they say? It actually goes into the idea that there is a supremum and an infimum on any of these subintervals. You have to assume something about your function. It's bounded. So we're assuming that we have a bounded function that is defined on this interval.
So it has to be defined on every point in the interval, right?
Exactly.
Okay, because if you have a one point where it's not defined, you can take that to be the partition and say it's
Right.
not defined.
Yes.
Okay.
And really it does go back to, well, why are you even asking? Your function's not defined, so why should anything else be defined? You know, if you can't even define your function, why should we be able to compute anything else? Now, we will get into improper integrals, because they actually play a role here. Now, we won't get into it fully, because to do so, I'd have to get you into the Lebesgue integral, and that would take us halfway through the semester. But we'll show you a little bit of what the Lebesgue integral looks like. But yeah, there is a question of, you know, when you deal with the improper integrals, and trying to figure out what should happen there when you have an unbounded function. Okay, and if you recall from calculus, you actually dealt with those. And you were actually able to find integrals of discontinuous functions that were bounded on an interval. You actually defined what the interval was. You didn't realize it at the time, but you were playing a little fast and loose with the whole definition of the interval. But we did. All right. So back to this one. We're assuming the function is defined on the interval. We're assuming it's bounded. Otherwise, we couldn't say that there must be a supremum or an infimum on any subinterval. All right. So we've got those requirements, but those don't seem restrictive at all. Just to say that it's defined and that it's bounded. I'm not really putting too many restrictions on this thing. All right. So not too bad now. So where's the catch? What's the problem? Every bounded function that's defined on this interval will have an upper sum and a lower sum. And they'll have an upper sum and a lower sum for any partition that I pick. Doesn't matter what partition. So where's the catch?
It's not.
Yeah.
If you do something like what we've done for that particular integral, you completely ignore all negatives.
Yeah. So here we ignored the negatives. Now when we went and go find the infimum, then we would be doing what? When we find the lower sum. Then these negatives would play a role. So when we start talking about this thing being an area, you're exactly right. We're not really talking about area the way we usually think of area. We're talking about what's known as a signed area. So if you have negative values, think of it as a negative area. Positive values, it's a positive area. All right, good. What other catches might there be?
If you just define the interval as pretty much the entire original interval, the subinterval is the whole interval, then you've got a really inaccurate.
Yeah.
So,
In fact,
Excellent.
the lower sum is pretty much going to be zero if it crosses.
Yeah. So the accuracy of our estimate here is going to be very dependent on the partition that we use. So there might be really good partitions that would, in fact, there might be partitions that get us, that land us, happen to just land us because we're lucky, right on the signed area of this curve, you know, between this curve and the x-axis. So just out of sheer luck, that happens. So some of them will be good, some of them will be really bad. So where's our definition of an integral in all of this?
So we find we have an upper integral and a lower integral,
Uh-huh.
and the upper integral is the,
So we have our upper sum,
yeah,
and then our lower sum.
and the upper integral is the infimum of of the upper limits of all possible partitions.
So if we find the, what you're saying is the infimum over all partitions of the upper sum, and then
Supremum over all the possible partitions
we
of the
find
lower sum.
the sup over all partitions of the lower sum, and where's our definition of the integral?
If those two are equal, that is equal to the Riemann sum.
If those end up being the same, then we call that value, whatever that turns out to be, the Riemann integral of our function. And we interpret it as the signed area, where areas below the x-axis are considered to be negative, areas above the x-axis are considered to be positive. Turns out that's a big if. Now, the antiderivative started having problems the moment you had a discontinuity in your function. So the question is, where does this if start having problems? Do you know of a function where that would not be true?
Would it be the weird function that they mentioned in the book?
The weird function that they
I don't
mentioned
know how to
in the
pronounce the guy.
Tomei's function, yeah, what was true of Tomei's function?
It's, I think it's continuous,
Yeah.
but yeah, I don't know how you make a partition such that you always get.
Yeah. How would you prove that something didn't have a Riemann in it?
Show that those can't approach each other.
Yeah,
So,
show that they can't get close.
so there's the Dildrich function, which was preceded the Tomei function that we talked about, where you always get 1 or 0, but in any interval you're going to have 1s or 0s. So that one you can show because the lower sum's always going to be 0, and the upper sum's always going to be consist of 1s.
Yeah.
And so that one won't be integrable.
Right. The Dirichlet function.
Yeah.
Yeah. So with, to remember what the function is, the Dirichlet function is,
We can make it simple.
we'll call it D. So X. It is 0 if X is.
I think it's irrational.
And it is 1, 0.
You say 1
What if
otherwise.
it's rational?
Yeah, it's 1 if it's rational. Okay, so that's right. So 0 if it's irrational, 1 if it's rational. We don't actually have a symbol for the irrational, we just write them as the rationals minus or the reals minus the rationals.
But, question.
Yeah.
If we flipped it though,
Yeah?
would it then be fine because the irrationals are uncountable?
Well, in any interval.
Well, we would still have the same issue, which is on any interval you have both rational and irrational numbers. And so your supremum is always going to be 1.
You're adding more.
And your infimum is going to be 0. And so your upper sums will always be 1, your lower sums will always be 0. Okay. So, how are we on the definition of Riemann integral? Okay with it? Okay, then let's move on. For Wednesday, read section 7.3. If I remember correctly. Yeah. We're going to be talking about integrating things with discontinuity.
Actually, that phone is actually so.
We'll also be able to grab that off
phone is
the
actually.
Yeah, the whole chapter, all of chapter 7 is actually.
Oh,
It's a PDF.
It's a Walmart phone.
Yeah. PDF for the whole chapter, so.
I know, but this is the worst one. The other phone, the charger cord broke.
What's your name?
Felipe.
Cool.
Is that good?
I am taking a longer time.
How's your break?
I'm taking a longer time.
Really?
But I took this last